Good morning. So my name is Nick. I am from the UK National Supercomputing Centre, part of the University of Edinburgh, and we have some massive supercomputers, such as this Cray machine up on the left. But if I'm honest, what I find even more incredible is all the infrastructure that goes around it. For instance, on the bottom right, all the plant to bring something like 40 megawatts of power to site, but then things like the tape libraries and all the robots as part of that to handle the data. And you heard me right, tape libraries. We've still got tape just because of the massive amount of data that's generated. And we're even more old school. About 65% of our codes, for instance, are written in Fortran, quite legacy. But even though I've said that, you'd be amazed at how scientific computing, HPC, touches the everyday. They call it the third methodology: experiment, theory, simulation. And about last 30, 40 years, every single scientific discovery has involved simulation to some extent. Some examples just from what I know here, for instance, on the top left, the molecular interaction of water and oil for better lubricants. The far right, simulations of jet engines. The bottom left is wind turbines and better wind turbines. Top middle, this is simulating plastic moving through the oceans. And then lastly, at the bottom middle, a stalwart of scientific computing, weather and climate, and this is the jet stream over the North Pole. Just to give you an idea of a few of the workloads. And we were really put to the test a few years ago with COVID, and a lot of the machines were being used to help form government policy. But the key challenge we face is the users are never happy. They also always want to run bigger systems, reduce time to solution, and we've been massively pushing to what we call exascale, 1 billion calculations per second. And there's a few machines out there now that can do this, but as I said, they always want more, they always want the next thing. But at the same time, the challenge we face is an increased focus on energy efficiency. We've got to power these new machines, and obviously the climate side as well. But also GPUs are becoming more expensive. There's more of a focus on that side towards AI and machine learning, so maybe moving away a little bit from what we need, and a huge amount of effort needs to port those legacy codes to those new accelerators. So when people say, well, what can RISC-V give you as the HPC community, I think the key high-level answer is one of choice. Because of the flexibility, the vendors can produce much more easily solutions that are suited to what we need, and we're not beholden, as we are at the moment, to just a couple of vendors and their own priorities and their own areas of focus. And I'm going to give you a few examples of that a little bit later on in the talk. But the question itself you've got to be careful with, because a modern supercomputer is hugely complicated. So when we're talking about RISC-V in HPC, there's lots of nuance how that actually might manifest itself going into the future and what we're currently looking at now. Now, over the past couple of years, and I was talking about this on Monday, we've seen a great progress in RISC-V for HPC. We've really had this mindset change over the past 18 months from can we do it to, OK, now let's look at the codes, let's look at optimizing the codes and really progressing this. And a stalwart for us has been the 64-core SG2042. It's the best high-performance part we've got. If I'm honest, it's showing its age a little bit now. This is, and the link to the paper is at the bottom, this is the next generation of that. And the benchmarking, there's loads of details, but really the takeaway there is the next generation of that has enabled us to move from what we had, the 2042, it's very similar performance to the Marvell Thunder X, up to the 44, similar performance to the Intel Skylake and closer to more modern processors. And what really excites me is what Andrea was saying yesterday in terms of the hardware that's coming online with RVA23 in this sort of next year. Because that, I think, is really going to help accelerate things. We've had some great progress so far, but really this could be the shot in the arm that we need to have this next generation hardware. And that's also crucially important because of NVIDIA's announcement to port CUDA to RISC-V. Critical for us in HPC, lots and lots of CUDA codes, but we need to have the CPUs there ready to be able to leverage that so we can have balanced systems from this. So my prediction is 2025 really could be a watershed moment for RISC-V and HPC. A phenomenal opportunity if what we've been talking about comes off and we bring these things together. Actually, quite a bit of what's been building, I think, could really, really accelerate there. Now, of course, the hardware itself isn't a huge amount of use without the software ecosystem. And we've been doing a lot of work in the HPC SIG to explore this and drive this. Just to maybe put a little bit of flesh on the bones, I looked at the most popular applications on our Cray supercomputer. This is the UK national supercomputer. And out of the ones I could sort of track and categorize, which is most of them, 35% of the runtime of the supercomputer are by applications which have been ported to RISC-V. They'll run on RISC-V, and people have announced this. And about 55% of the applications themselves, users using these applications, have a port for RISC-V. Now, of course, it's more nuanced than that. There's, how optimized is it? How maintained is that fork and all of that? But if I'm honest, I was actually quite pleasantly surprised at how high these numbers were. And a lot of this sort of hides the underlying complexity of the key technologies, the compilers, the communication technologies, some of the other bits and pieces that have been brought over to enable this top-level thing. Now, there's some real standout activities going on. Barcelona are a great leader here in terms of picking these applications and then really being able to drive the optimization. And they gave a fabulous talk to the HPC SIG a bit earlier in the year in terms of all the lessons that they've learnt. That's up on our SIG Confluence page, and we've also teased out really the key headline points. But it gives you an idea of, we're really looking at building this in the community and bringing that knowledge together to make this as easy as possible. The CPU side is one thing. The accelerator side is the other side to this. And potentially, this is an easier proposition for HPC because I can take an existing system and slot this in to the PCI Express slot. I maybe don't need everything changed. But this is also a fabulous example of the choice and the flexibility. For instance, that accelerator at the bottom right by Caligo, an Indian company, what they've done is they have provided for the first time something called posits. In HPC, for many years, we've been talking about this alternative number representation called posits. We never had a hardware implementation of it. So they've taken RISC-V CPU, they've developed their posits IP, they've put it together, and now, for the first time, that community can actually run codes on this. Been a massive shot in the arm. Our biggest conference in about a month's time in HPC, they've got a dedicated workshop with this hardware there, being really able to drive that. The bottom left, Inspire Semi, and Doug is here at the summit this week with physical chips. The approach they've taken is to say, look, HPC first, FP64, and really designing this with the programmer in mind to be able to very easily port codes over, run those really common HPC technologies on this as a first-class citizen. Again, a great example of the flexibility on wanting to focus in one specific area. And I'm hugely excited about this. They're going to have wide production available technologies early next year, from what I understand. And then lastly, to highlight Tens Torrent. I don't know if you've been to their booth and played Doom. I think they've made it more difficult because my score 30-odd years ago was a lot higher than I got yesterday. So my takeaway is to go home and practice on Doom. But in all seriousness, they have produced a whole bunch of accelerator cards designed for AI, but opened up the ecosystem so we can use them more widely for scientific computing and HPC. And a whole bunch of groups have picked this up and have been going with this. In Edinburgh, we've been porting a whole load of applications to their wormhole card. For instance, this is Fourier transforms, utterly key across a whole bunch of different codes. Really quite interesting because of the memory access pattern. Lots of details in the paper. The performance I'm not quite happy with. I think we can improve on this. But even at that performance level, in terms of overall energy efficiency, energy to solution, it's something like 3.5 times better than a Xeon Platinum CPU, and actually a lot cheaper as well, which is incredible. And bottom here, E4 Computer Engineering, they've ported N-body simulation, very heavily used in astrophysics. Again, over to the wormhole. Incredible results, 2 times faster, 2 times more energy efficient. And again, I've just linked to their paper where they talk about that and all the techniques. And now we've got the black hole in our hands as the community. And this is just a couple of points to highlight with a much wider range of things going on, really looking at these and driving these. But again, it goes back to this benefit of the openness, the benefit of the flexibility, and the fact that we in the HPC community are actually really keen to pick these up, to kick the tires of them, to develop the algorithms, and progress this forwards. Now, we've been doing a gap analysis in the HPC SIG, and I'll link to it on my next and last slide. And we've been looking at the entire ecosystem and really what we need to improve, what's working well as it currently is. And we've highlighted a couple of key things. Firstly, the software tooling. I think we're making good progress on the open source side, sometimes with more commercial software, so some of these commercial simulation codes, some of these commercial tools like some of the profilers and debuggers we use very heavily in HPC. It's a bit more of a challenge to make the case to those companies that there'll be a return on investment there. And again, and we were talking about this in the ambassador thing this morning, I think part of this is getting that new generation of RV23 hardware so they can actually see that there's hardware to run on that's very, very competitive. Also, things like convincing the vendors to release cluster management tools for RISC-V. Now, in terms of scaling out, we've not really looked at this in any serious detail when we're doing our benchmarking so far, because a lot of these technologies have quite basic Ethernet, or from our perspective, quite basic Ethernet on them. There's a lot more high-performance things, high-performance networking. In theory, a lot of the building blocks are there, and some groups, such as tactical computing, have done some great work sort of playing with some of the drivers, but still we need to drive that maturity, and we need to explore this and demonstrate that. And sort of hand-in-glove file systems. Again, there's some nice initial work here. I've seen some latest results where we can actually run things such as Lustre, which is a big high-performance parallel file system, but then a lot of consideration needed in terms of the optimization and the best practice there. And of course, on the GPU side, hugely exciting getting CUDA over to it. I think it's then going to be a really interesting journey to, again, explore kicking the tires and really seeing what we can do out of this on RISC-V in the community. And lastly, it's been talked about throughout the conference, the matrix extensions, yes, they're designed for AI and machine learning, but actually circling back to some of these accelerators like the wormhole, what we've discovered is with a whole bunch of HPC applications, by redesigning them, we can actually really leverage these building blocks and some of the work provided there. So again, it's really understanding how we exploit that and where things might not quite be perfect, and we then need to influence sort of version 2 of those standards, as well as I say, improving the algorithms. So really, my last slide is a call to action. I have seen over the past couple of years a huge amount of growth in the interest from the HPC community in RISC-V. If I'm honest, a couple of years ago, maybe not taking us that seriously, to now much, much more serious proposition into the future. But there's still a lot to do. I think we've done a great job of highlighting some of the potential benefits, but we've got to be ready when the hardware is there with everything else and with the ecosystem. I mentioned the gap analysis we've done. This is up on the SIG Confluence page. It'd be great to get your opinions and view of that. We're also collating HPC benchmarks. And the idea of this is when vendors come out with new hardware, we can say, well, look at these benchmarks, run these, this is what we care about, and actually you can see what the different benchmarks mean in terms of the wider performance we might get for HPC. And there's been some fabulous feedback and discussions about these this week. So really, a call to action, get involved in the SIG. It would be great to have your knowledge and expertise. It would be great to have your views and what you consider here. And lastly, if I whet your appetite, in EPCC in Edinburgh, we have one of the RISC-V ecosystem labs. It's set up as an HPC RISC-V testbed, free access. It lets you go on. It feels like a supercomputer, but all the compute nodes are RISC-V. So again, kicking the tires, being able to explore the technology, and a lot of this has been used to do some of the benchmarking and things that we talk about in this talk and elsewhere. So thanks for listening, and beyond this, I'd love to have a chat more generally. Thank you.